let's take a look at the assignment sheet so you can kind of get an idea of what's going on with us. So you'll see on your assignment sheet, I've included what we did before break, because what we learned right before break is part of this unit. So that's why those boxes are already crossed out, because I've already checked the homework for that, so I'm not going to make you pull that back out and check for homework again. So back on the 13th, we learned about relationships within triangles. That's what we reviewed last class. Is it acute, obtuse, or a right angle? Can it make a triangle? What are the possible side or possible links for a third side of a triangle? Things like that. And we took our quiz over factoring in day one. I do have those graded. I don't have them to get back to you yet, but those grades will be on soon. And then last class, we learned about our perpendicular bisector and angle bisector theorems, and your homework was that worksheet 1. And then we were blessed with a snow day, which was very exciting. And so now everything's just going to get shifted, basically. So today we're learning about points of concurrency with perpendicular and angle bisectors and review of mid-segments. So this should say mid-segments. And then next class, we'll do points of concurrency with altitudes, and this should say medians. Sorry, flopped my vocab. So we already learned about mid-segments last unit. We're going to be incorporating that into our unit again for this unit. So we'll recap that today and talk about points of concurrency. And so that's what you were just working on with your vocab for your warm-up, was that you were going ahead and defining what those points of concurrencies are. So we'll learn about a couple of them today, particular theorems we have with it, and a couple more next class. So it's actually a pretty short unit, and that's really about 4 days of instruction. So then that's putting our test at the 18th. If we happen to miss school between now and then, we should still be able to get this in before the end of the quarter. But if we get 6 feet of snow, that'd be great. We might have to adjust accordingly, but I think we should be fine regardless if we miss another day or something. All right, any questions with the pacing? Okay. So again, reminder, if you didn't have your homework for today, just show me that next class. All right, but let's go ahead and take a look at your homework. All right, so what I just passed out to you should look like this. And it says points of concurrency and review of mid-segments. So again, we're looking more at what happens when our perpendicular bisectors meet together and what happens when our angle bisectors meet together. Before we do that, though, I want to actually go ahead and jump to the end of the notes. I'm going out of order here. Go ahead and go to that triangle mid-segment theorem. This we've already learned in a previous unit, but it is coming back into this unit again, so I just want to make sure that we remember this from before. And that will agree with it. All right, our triangle mid-segment theorem. First of all, what is a mid-segment? Who remembers what that segment is? I know it's been like almost a week since I've seen you guys.
Isn't it parallel to the bottom of the triangle and this is split into two?
You're close. So one of our properties from our theorem is that it is parallel. Now a mid-segment itself is that it joins the midpoints. So go ahead and draw on your picture. If I have that AB and AE are congruent, then that means that A is the midpoint of that side EB. And likewise, BC and CD are congruent. That means that C is the midpoint of that side. So your mid-segment is simply the segment that joins the midpoints. Okay, so this is our mid-segment. And we talked about this last class when we were doing our vocab. How many mid-segments do I have in a triangle? 3. Because I can go ahead and draw, and if I fill my midpoint here, connecting these two midpoints, that's another mid-segment. And connecting these two midpoints, that's another mid-segment.
Now you have 4 triangles.
Now we have 4 triangles all within that big triangle, indeed. Okay, so Lucy already touched a bit on what the theorem tells us about that mid-segment. So let's go ahead and formally write it out. Alright, our triangle mid-segment theorem. If a segment joins the midpoints of two sides of a triangle. So if a segment joins the midpoints of two sides of a triangle, and what do we call that again? That joins the midpoints? Midsegments. So I'm going to go and put that in parentheses just so you remember that vocab word. Alright, so if a segment joins the midpoints of two sides of a triangle, then the segment is parallel to the third side. And the segment is parallel to the third side. And does anyone remember what that second characteristic is? Okay.
Well, I know that AC is like half of the empty.
Yeah, very good. So our midsegment is half the length of the third side. So it's parallel to the third side, and it's half the length of the third side. And is half the length of the third side. Good. So that was our theorem that we learned before. So our triangle midsegment theorem. And again, we have two characteristics. My midsegment is parallel to this third side, and it's half the length. So I'm going to go and write that in. AC, segment AC is parallel to segment ED. And we also know that the measure of AC is equal to 1/2 the measure of ED. Alright, so let's go take a look just at those few examples here. So if AC, the measure of AC is 5 inches, what's the measure of ED? 10 inches. Good, make sure you give your units. Alright, and then example 2, if the measure of angle BCA is 65 degrees, then what is the measure of angle CDE? Yeah, 65 degrees. How did we know that? They're parallel lines, and thus their corresponding angles. Good. So corresponding angles positive. Tells us that. Very good. All right. So example 3, AC is well, we kind of already said this, is parallel to ED. Make sure you use proper notation there. And therefore, angle BAC is congruent to angle what? AED. Yeah, you could say either BED, AED, or I'm just going to call it angle E because that's the only angle there, right? So I'm going to go and just say angle E. Because, and we already talked about this, corresponding angles positive. Good. Questions so far? Notes review, it's pretty basic. Trying to warm up your brain since it's been a while. Alright, I want you guys to go ahead and try example 4 here. They give you an expression for AC, they give you an expression for ED. What is X? Go ahead and solve for X. That one. Didn't you miss that sound? And once you have your answer, go and check with your shoulder partner, see if you got the same thing. Alright, what did we get for X?
30.
30, good. So my beginning equation, what I know from my theorem is that, again, the measure of AC equals 1/2 measure of ED. And then I can go and put in my expressions. What's another way that I could have started out, rather than saying AC is half of ED? What could I have done instead? Come on.
ED equals 2 AC.
Yeah, I could have just doubled AC and let that equal ED. And then I would have just put in my expressions. AC is 2x plus 5. ED is 5x minus 20. Don't forget to distribute, and then you just go from there. Good. So it's totally up to you, whichever one of these you use. I like to not deal with the fraction if I don't have to, so it's pretty tough. All right, questions on this? Again, pretty easy. All right, let's go and flip it back to the front side, and I'll go into normal ones. All right, concurrency of perpendicular bisectors theorem. What does that mean again for lines to be concurrent?
There are three or more lines that meet in one particular point at which they of hundred.
Ooh, what a great definition. How kind of someone to give that to you. Good, so from our vocab we learned last class that if we have 3 lines that meet at one single point, then we call those lines concurrent. They all occur at the same time at one single point. So concurrency of perpendicular bisectors, that means we're talking about our perpendicular bisectors. How many perpendicular bisectors can I have in a triangle? 3. So what this theorem is telling us is saying, hey, when we draw our perpendicular bisectors, they all meet at one single point. And we'll talk about what that's called, and there's a specific property that this point has. All right. So concurrency of perpendicular bisector theorem. The perpendicular bisectors of a triangle intersect at a point and I'm going to leave parentheses with a gap because I'm going to fill in what that is in just a moment. Alright, so our perpendicular bisectors all meet at a point within that triangle. And this point is equidistant, so that is equidistant from the vertices. Alright, so we have, if I've drawn all 3 perpendicular bisectors, they're going to meet at one single point. And that single point has a special characteristic or special property that is equidistant from the vertices. It's the same distance from each of my vertexes. So what is that point called where the perpendicular bisectors meet? You did this in your vocab, so if you need to look back at your vocab, when we're dealing with perpendicular bisectors, I mean, what's it called? Okay?
Essentially.
Careful, we want perpendicular bisectors.
Circumcenter.
Circumcenter. Circumcenter. Circumcenter. So our vocab I don't know that I have it on my should say something about our perpendicular bisectors meet at one point. So the point of concurrency of the perpendicular bisectors of a triangle is called the circumcenter of the triangle. You need to know that vocab word, and you need to know that it corresponds with our perpendicular bisectors. Alright. So this picture here is nice, and everything is drawn in. We have our perpendicular bisectors are drawn in. You can see that with our red lines here. We know that they're perpendicular bisectors because they are perpendicular, and we see that it cuts these sides in half. So that allows me to know that these are perpendicular bisectors without it stating it. We see that from the symbols on the page. So I see my 3 red lines here intersect at one single point, and that point P is my circumcenter. So what this theorem tells me, in this picture here, if P is the circumcenter of triangle ABC, then according to this theorem it says the circumcenter is equidistant from the vertices. Well, my vertices are just those points where the corners of the triangle, if you would. So what I have then is from the circumcenter to the vertex, so the distance from P to A, is going to be the same as the distance from P to B, which is the same as the distance from P to C. So that circumcenter is the same distance from each of the vertices. Let's see if my smartboard will work with me today. Yes! Alright, so I'm going to go ahead and highlight those. Feel free to do so on your notes as well. Whether you use highlighter or different color pen or something to make that stand out. Those dotted lines are essentially the conclusion from the theorem. My dotted lines are showing me, my dotted lines are the distances that are the same length. So notice, I only have information that the circumcenter is the same distance from the vertices. I don't know that it's the same distance from the sides. And in fact, if we look at this picture, it's pretty clear that this distance is not the same distance. But no matter what type of triangle I have, in any triangle, your circumcenter will be the same distance from each of the vertices. Okay, so that's your big takeaway with our theorem here. Now, we do have three different types of triangles: acute, right, and obtuse. And depending on what type of triangle you have, will determine where your circumcenter falls. So I went ahead and copied this diagram from the book because I feel like it draws it out real nicely for us. If I have an acute triangle, I can see that my circumcenter is inside my triangle. Whereas if I have a right triangle, it ends up being on the triangle. Ends up being on one of the sides of the triangle. And with an obtuse triangle, it ends up falling outside of my triangle. And this is true for each of these categories. Regardless of what kind of acute triangle I have, my circumcenter will always be inside. Regardless of what kind of right triangle, my circumcenter will always lie on it, and regardless of what type of obtuse, it will always lie outside. So my circumcenter could be in, out, or on my triangle, depending on what type of triangle I have. Alright, questions with this information so far? Okay. So let's go take a look at this next chart. It says coordinate geometry, and we're going to have this keep introducing, keep on reappearing in our notes of the different types of lines that we have in our triangle. And so we have, so far we've done where we have a picture where the line's already drawn in for us. We can see where that circumcenter is. But sometimes they might give us just coordinate points on the graph, and we have to identify where that circumcenter falls. Now, example one's pretty nice because it's drawn out for us, and it happens to be that two of our sides are a nice vertical and horizontal line. In example 2, they didn't give it to us drawn out, but they did give us the coordinate points for us. And if we flip it over, example 3, they drew it out for us, but we see only one of them is a nice horizontal or vertical line. So we're going to have to find the circumcenter based upon those coordinate points, and it does require us to revisit the lovely world of Algebra 1. Alright, so let's go ahead and tackle all of these examples here. Now, example 1's not too bad. So it says find the circumcenter of the following triangles. Now, the theorem that we had just told us that all three perpendicular bisectors are going to meet at that circumcenter. So in order to find the circumcenter, I don't have to find all three of them. I can just find two of them, right? Because we know that third one will meet at the same point. So I don't have to do all three perpendicular bisectors. I could just do two of them and then find their intersection. So that saves us a little bit of time. Alright, so for our first example here, I could find the perpendicular bisector of this hypotenuse, but that's going to be more work than just doing the vertical and horizontal lines. So I'd say let's go ahead and do our perpendicular bisectors of these guys. Alright. So before we do this, let's talk about what does the perpendicular bisector have to do. What is one thing my perpendicular bisector has to do? How do I know if it is a perpendicular bisector? Come on. Yeah, it hits the midpoint, right? It cuts it in half. So it goes through the midpoint. Now, once again, it's pretty easy to find my midpoint of this side here. But say I was trying to find the midpoint of this guy. How do we find the midpoint if we don't have a picture? What do we have to do? The formula! Remember back in August or September, before snow was even a thought in your mind? We had a midpoint formula. My midpoint formula was the sum of my x's divided by 2. That gave me my x coordinate. And then the sum of my y's divided by 2. That was my y coordinate. Alright, what's the other characteristic of perpendicular bisectors? It has to go through the midpoint. What else must it do? Go ahead, Emma.
It must be perpendicular to the lines bisecting.
Very good. It must be perpendicular bisector to the lines bisecting. Since we're talking specifically about triangles here, I'm just going to say perpendicular to the side, because we're going through the sides of the triangle. Now, once again, for this picture, it's pretty easy for me to see that perpendicular is going to be a horizontal line for that one. But say I was trying to find the perpendicular line to my blue side. That's going to be a little bit harder to do. And again, sometimes I don't have a picture. I only have coordinates. So what do I know about two lines that are perpendicular? In the world of algebra, what do I know about those two lines?
Their slopes are opposite.
Very good. Their slopes are opposite and reciprocal. Good. So slope is opposite and reciprocal. So we want to keep these in mind as we're trying to find our perpendicular bisector. Again, sometimes it's easy to do from our picture, but sometimes we might have to do a little more. Okay, so now the last piece, though, is say I do end up finding my two perpendicular bisectors. How do I know when they intersect? Because again, on a picture, it might be pretty easy for us. But let's say that my equations for my perpendicular bisectors end up being y equals 2x plus 3. I don't know, y equals 2/5. Let's go negative 2/5 minus 5. What if these were the two lines that I was trying to find when they intersect? How in the world do I find when these lines intersect? Come on. Where they equal each other. How do I do that? And what is that method called? It is solving using a particular method. So we're solving a system of equations by using substitution. Or you could use elimination, but probably most of you would prefer to do substitution for this. So we would want to find where they intersect, which would require us to use Algebra 1, solve the system with either substitution or elimination. Okay, so just keep that in mind, because again, this is the world of Algebra 1 that we are entering into. Alright. So that's kind of the general idea of what we'll be doing with these. Now again, some of these are going to be easier than having to do all that. So for example 1 here, I'm going to take a look at this vertical side. Again, it's pretty easy for my picture to see that my midpoint is going to be right here, because there's only length of 2. And since this was a vertical line, my perpendicular bisector is going to be the horizontal. So let's go and write out what that equation is. This is y equals, what's my slope for this guy? My perpendicular bisector. 0, right? What's my y-intercept? Just a regular 2, right? So do you agree my equation is y equals 2? Also from Algebra 1 we had those acronyms BUCS. Boy, do you remember those? Okay. So for those that don't remember, BUCS, vertical lines have undefined slope, and their equations are x equal. Horizontal lines have a slope of 0, and their equations are y equals. My perpendicular bisector here is a horizontal line, and so I have this y equals just about it. Okay, so that one was pretty easy. Let's take a look at this side here. What is my midpoint going to be for that one? What is it?
3.5.
Good, 3.5. So a little bit trickier because it fell partway in between. And again, since this is a horizontal, it's pretty easy to find the perpendicular line. It's just going to be a vertical one. Draw that perpendicular. Alright, so it's a vertical perpendicular bisector. So vertical lines are in the form x equals, my slope is indeed undefined, and so what is this equation going to be? X equal to 3.5, just that midpoint. Now we can see that my circumcenter ends up lying right on the triangle, which makes sense because this is a right triangle. Alright, so we're really just one step away. Now we have to find where these two lines intersect. We could do a system of equations, but really, doesn't it just give us the answer there? So our answer ends up being 3.5 and 2. Not too bad. Questions with that one? So now for example 2, they did not give us a picture, they just gave us the coordinate points. I think it's often helpful to go and sketch a rough picture of it just to get an idea of what's going on. Alright, so A is at 5, 2. B is at negative 1, 2. Notice they're at the same height. And C is at negative 1, negative 3. And so we have something like this. And again, conveniently, we see that A and B were at the same heights, and B and C were at the same, I don't know, to the left. So fortunately for this one, we do have another vertical and horizontal line. Okay. Now we are still going to need to find our midpoint, but then from there it's going to be pretty much the same as example 1. So go ahead and give this a try, example 2. If you want to do the midpoint formula, that's fine, to go and find where your midpoints are for each of those. But I want you to go ahead and find that circumcenter for example 2 here. And feel free to work with your shoulder partner. Talk with them. Introduce yourself again if you forget who everyone is, because it's been a while. But go ahead and work together on example 2. See what you get. Alright, so ideally you probably compared your perpendicular bisector for AB and your perpendicular bisector for BC. Now you could have done for the line AC, you just would have had a little bit more work.
Wait, what if you did
BC, yeah. Perpendicular bisector for BC. It's not necessarily going to be going to the midpoint of that. Good question. Okay, so I'm going to start off with segment AB, because I need to find out some information about that. Right? So I know that my perpendicular bisector must go through the midpoint. So first, let's identify our midpoint for this. And again, my midpoint, I add the x's together, so I'm looking at just my segment AB. So I add my x's together, divide by 2, add my y's together, divide by 2, and let's see. So we get 5 and negative 1, so 4 divided by 2, so 2. And 2 plus 2 is 4 divided by 2 is 2. Did we get a midpoint of 2, 2 for that one? Okay. So that gets me a starting point. I know that my midpoint is the point 2, 2. It has to go through there, right? Alright, now I also know that it needs to be perpendicular. So this was a horizontal segment. So my perpendicular bisector is going to be a vertical segment. What type of equation do I have if it's vertical? Is it x equals or y equals? X equals. Okay. So my perpendicular bisector is going to be an x equals equation, and x equal to what? 2. That's what it's going through, right? It's going to be this vertical line going through that midpoint. Alright, sweet. So we found our perpendicular bisector for one of them. Now let's go ahead and do that for our other side. Alright, so I'm going to deal with side BC. So once again, I have to find my midpoint because I need to know what is that point it's going through. And so BC, I'm looking at my midpoint here. -1, -1 is -2 divided by 2. So -1. And then I have 2 plus -3 divided by 2 is -1/2. Do we agree with that as our midpoint?
Wait, I thought you had to find one.
What's that?
You have to find the intercept of all three.
Well, I need to find where my perpendicular bisectors intersect. So I first start off by finding my perpendicular bisector of AB, which I need the midpoint for that.
The midpoint. I thought the midpoint was opposite.
Yeah. So my perpendicular bisector goes through the midpoint. So I need to start off by finding my midpoint, and then I can write the equation of the line that goes through there. So I'm doing that with 2 of the sides. You can do it with all 3, but you only need 2. Alright, so are we good with that midpoint? Okay. And then if I look here, again I see that my perpendicular bisector is now a horizontal line. What type of equation is that going to be? Y equals. And y equal to what? -1/2. Alright, so I see then that this line is y equal to -1/2. This is x equal to 2. So what must my circumcenter be? Okay, just those 2 values. Okay. My circumcenter is at the point 2, -1/2. Now please, when you do this, go back and do a quick check. I don't want you to do all this work and then in the end get it wrong because you flip-flopped your x and y values. So make sure you put your x value first and your y value. Okay?
How come you just don't, why don't you just like find the midpoint of AC if it's a right triangle?
So that's not going to be the case for all triangles. Because if we take a look at our next one here, my midpoint's not just simply going to be, my circumcenter is not just simply going to be the midpoint of one of the sides. Now, we've seen that's happened for our right triangles, right? But we don't have that happens for all of them.
Well, except for right triangles.
Oh, for right triangles? Yeah, that would actually end up working because you have that it crosses at those 2 points. Yeah, that would be fine. But just keep in mind that doesn't work for triangles in general. Alright, questions with this? Okay. And again, I know for most of you, you're able to do quite a bit of this in your head, particularly when they give you a picture. But when it's not nice and easy, then you know. Alright, let's go take a look at that last one, where they throw a little bit more at us. So we only have one horizontal line to work with, so we do have to do a little bit more work. The question says, where should the farmer place the hay bale so that it is equidistant from the 3 gates? Alright, so we have the 3 gates plotted on our graph, and they want to know where should he put the hay bale. Do you guys know what a hay bale is? Okay, good. And you know what a farmer is, right? I don't know, we're out here in the city, just want to make sure we're good. The guy that tends to the animals, the cows and whatnot, those are the ones that go moo, give us milk. Alright, so we want the hay bale to be equidistant from the gates, which means it's equidistant from the vertices, so we're looking for that circumcenter. Now, again, we have one nice and easy side to work with, but then we're going to have to choose one of our other sides, which won't be so nice and easy to work with. But it's still not too bad. So let's first go ahead and find our perpendicular bisector of this red line here. Where's my midpoint?
0.
Yeah, it's located at 0, 0. And if I go ahead and draw on my perpendicular bisector, do you guys agree that that's just the line x equal to 0? Okay, so that one wasn't too bad. Now, for the ones that require some actual work. You can choose which of the other two sides of the triangle you use. I'm just going to go ahead and use this side here. So I'm going to call it my blue side. And again, I need to know where the midpoint is and what the new slope of the line is. So let's go ahead and find our midpoint of the blue line here. All right, so I'm going to write in what these coordinate points are. It just makes it easier for me to calculate my midpoint. So it's -3, 0. This is 0, 5. All right, so what do we end up getting for my midpoint? What's my x value? -3/2. Don't forget your negative there. And my y value? 5/2. Oh, how nice! They gave us fractions. Okay. So I have my midpoint, and I'm going to try to approximately draw that out there. And I know that my perpendicular bisector must go through. But again, in order to know the slope, I need to do opposite reciprocal. So first, let's find what our actual slope is. What is our actual slope of that line? What is my slope of this line? Do we know? Go and check on your paper. Up 1, 2, 3, 4, 5. 5/3. That's not nice either, is it? That's all right. Okay, so that's the slope of the original line. So what's going to be my slope of my perpendicular line? Negative. Okay. So now we can go and write our equation of our perpendicular bisector. We have a point that it goes through, the midpoint, and we have the slope of that line. How do I write the equation given a point and the slope? Point slope form. All right. Now you can use whatever equation you want, but I think that's going to be easiest. So I'm going to go and write my equation. So y minus my y value equals slope times x minus my x value, which is being plus 3. So what we just found here, this is my equation of the perpendicular bisector for that from A to C. Okay, now we can definitely simplify this. Yes?
You got the negative.
Well, it's minus a -3/2, so it became the plus. Thank you. Are we all good with how this equation came about? Questions so far? Okay. So we can go ahead and simplify this sum, but I want to take a look at what we're going to do now. So I have, here's one equation for my perpendicular bisector. And here's my other equation for my perpendicular bisectors. I just need to find where these intersect. So don't I just do a system of equations? Now again, I can simplify this one here, make it a little bit nicer. But I have two equations. I just need to find where they occur at the same time. Conveniently, x equals 0. That's pretty nice for substitution, because then I can just take 0 and put it in for x. I know that my circumcenter will have to be of x value 0 somewhere. So it's up to you. You can simplify this first and then substitute in, or just substitute in right away. But we're just going to use substitution to help us solve here. I think I'm going to go ahead and just substitute in, because that, since x is 0, that allows me to eliminate a little bit. So I'm going to go ahead and substitute in, and let's see, we end up getting y minus 5/2 equals -3/5. When we just have 3 halves inside here. Are we good with that? Okay. And then we just solve from here. Y minus 5/2 equals -9/10. Oh, that looks great. Alright. You can add 5/2 and you have to get a common denominator. I'm going to go multiply by 10 on both sides. You're more than welcome to do a common denominator. You guys go and solve. I'll solve. Let's see if we get the same thing. I personally just don't like to deal with fractions if I don't have to. Actually, I'm going to write that. So go ahead and solve for y.
I have a question.
Yes.
So, like, where did this equation come from?
This one here.
Like, I found the circumcenter, I just don't know what to do after that.
How did you find your circumcenter?
Wait, I did the midpoint of the gate 8, gate C, yeah. Negative 3 halves and 5 halves.
Yep, this guy here.
Yeah. And then I got the midpoint of B and C, which is 0, 0.
Yep, that's this guy here.
Technically, I just substituted those one way. I said it's circumcenter of 0 and 5 halves.
So you're saying that my circumcenter is at this point and at that same height.
Yeah.
That's not the case because we don't have, what we had before is that where those lines intersected was going to be the, if you would, the width and the height of that point. Because it was a horizontal and vertical line. Where horizontal and vertical line intersect are just the values of that horizontal and vertical line. But here we don't have just a horizontal and vertical line. We have a vertical line and then some type of slanted line here. So I need to find where these two lines intersect. Well, from Algebra 1, we know two lines intersect when those lines are equal to each other. So we're just doing a system of equations. So we got our midpoint, we got our slope, and we wrote this here, just using Algebra 1, writing our equation of the line. So what this equation here is this perpendicular bisector here. That's my equation of this perpendicular bisector. So now I'm just simply finding this point here. Where does this perpendicular bisector and this perpendicular bisector meet? Well, Algebra 1 tells us two lines meet where they're equal, so we're just using substitution. That's why we're taking the green box equation and this green box equation here and substituting them into each other. Now, sometimes we have an actual, for this one it was just x equal to 0, sometimes there's also a y. But since there wasn't a y, we could just go and take 0 and substitute it in for 0, or substitute it in for x over there. So we're just doing a system of equations with our two perpendicular bisector lines. But we had to first find those equations of the lines. So we're using Algebra 1 to find our equation of the line, and then Algebra 1 to find where they intersect, which we have to do substitution or elimination. Here, substitution. Does that make more sense? Okay, so I want to make sure we're not making that same mistake that your circumcenter is not just simply the midpoints combined together. No, our circumcenter is where the perpendicular bisectors intersect. So we have to find our midpoints to find the equation of the line, and then where those intersect, that's my circumcenter. So you must first find your equation of the line for each perpendicular bisector, then solve that. It does require you to do Algebra 1 a couple different times, but you have to first find your equation of the line and then find where they intersect. And when they intersect, typically will require you to use substitution. Questions with that? So what we're doing right now is just simply substituting x equal to 0 into my other equation for the bisector here. So
after you find the midpoints, what's the next step?
So that's the point that the bisector goes through. So for any equation of the line, I need a point and the slope. When you find your midpoint, you just found a point, so you need to find your slope. That's why I found the slope to be opposite reciprocal, because then it would be perpendicular. Does that make sense? So it's perpendicular, and it goes to the midpoint. Other questions with that? Okay. All right, I'm going to go and finish out finding what my y value is. It looks like it's going to be a kind of nasty fraction, which is fine. I got the value of y equals 8/5. Anyone else get that as well? Awesome. Okay. So what we just found is that our solution to this system of equations, the point at which our perpendicular bisectors meet, the point at which this line and this line intersect, is the point x equals 0, and y is 8/5. And that's our circumcenter. So again, these types of problems definitely take some work, because it requires you to first find the equation of the line. And that equation that you're finding is the equation of the perpendicular bisector, which goes through your midpoint and is perpendicular. So you first have to find your midpoint and then find that perpendicular slope. Once you have found those equations of the line, which again was our green boxes here, then you just do a system of equations from there. You could use substitution or elimination. For this one, substitution. You solve, and that's your second. Questions with that? Okay. So let's take a look. That was all with our perpendicular bisectors. Again, just recapping real quick. What our theorem tells us is that our perpendicular bisectors meet at a single point, and we call that our circumcenter. Turn to your shoulder partner and say circumcenter. Circumcenter. Okay, keep that ingrained in your brain. And our circumcenter is the same distance from the vertices. Okay, so now let's take a look at what it is for angle bisectors. That's our next piece here. Alright, I'm going to move this. Alright, so again, your angle bisectors, you looked at this vocab word for part of your warm-up. So we have concurrency of angle bisector theorem. Again, we have our angle bisectors all meet at one point, and we call this particular point something, and there is a special characteristic about this one as well. Alright, so concurrency of angle bisectors. How many angle bisectors do we have in a triangle?
3.
3. Okay, so all 3 meet at one point. Alright. If a point, oh, sorry, wrong one again. The angle bisectors of a triangle meet at a point, and once again I'm going to leave a parentheses, empty parentheses, because we're writing what that word is in just a moment. Okay, so the angle bisectors meet at a point that is equidistant from the sides of the triangle. Alright, so the angle bisectors meet at a point that is equidistant from the sides of the triangle. So it's kind of similar to perpendicular bisectors in that it's equidistant, but it's equidistant from the sides rather than from the vertices. Alright, so let's fill in this vocab word. The point of concurrency of the angle bisectors of a triangle is called what? Cameron?
Incenter.
Good, the incenter. So go and fill it in down here and in our theorem. So in other words, your theorem says the incenter is equidistant from the sides. Alright, so once again in our picture here, very nicely drawn in are our angle bisectors. And I know that these are my angle bisectors because I can see these markings that indicate the angle is cut in half. And we see that all 3 meet at a single point. And this point at which they meet is called my incenter. So again, another vocab word you need to know. Angle bisectors meet at the incenter. Okay, so if P is the incenter, the incenter of our triangle, and this triangle is also ABC. Then what our theorem tells us is that P will be the same distance from the sides. Remember, when we talk about distance from a segment, from a point to a segment, we're talking about that shortest distance, which is the perpendicular distance. So you'll notice each of these are perpendicular. Notice it's not necessarily perpendicular bisector, because it doesn't cut in half, but it is perpendicular. So our theorem says that this incenter, P, is the same distance from each of the sides. So if P is the incenter, then the distance from P to X will be the same as the distance from P to Y, which will be the same distance from P to Z. And once again, let's go and get out a highlighter, different color pen, or something to make that stand out to us. So this distance to the sides are the same. Once again, I don't know any information about the distance of the vertices here. I only know the information about the distance to the sides. We see that each of those are perpendicular. So when you're given a picture with a bunch of stuff drawn in, first identify what has been given to you. Here I can see I've been given angle bisectors, not perpendicular bisectors, because these are perpendicular, but they don't cut in half. I see I've been given angle bisectors, which allows me to identify that as the incenter. Then I can know that the incenter is going to be the same distance. Alright, now a key thing here, we have with our circumcenter that we looked at acute triangles, right triangles, and obtuse triangles. Well, for the angle bisectors, meaning that the incenter, it actually has a unique property that the incenter is always going to be inside of the triangle. So let's just go and write that as a note here. Incenter is always inside the triangle. So the incenter is always inside the triangle. And that's pretty nice because it's called the incenter, it's inside the triangle. And if we think about it, since it's based upon my angle bisectors, those will always be inside the triangle. The intersection will always be inside as well. So regardless of whether it's acute, right, or obtuse, it will be inside. Questions with that? Iman, did you have a question?
No.
Alright, so again, the two big concepts for today is that our perpendicular bisectors meet at the circumcenter, which is the same distance to each of the vertices. Our angle bisectors meet at the incenter, which is the same distance from the sides. Now, next class, we're going to learn about our medians meeting and our altitudes meeting, which means we're going to have a lot of new information coming our way. So there are a couple acronyms that I use. Don't put your stuff away. My goodness, we still have like 25 minutes, guys. There are a few acronyms that I use to help you remember. Oh my goodness, are we leaving soon? Good, we still have 5 minutes. That's good, I only needed 5. I was still thinking 50. I'm looking at the clock and I'm hungry. Alright, so there are a couple of acronyms that I use to help me remember this. Now, they're far-fetched to say the least. Feel free to use them, feel free to reject them, and come up with your own. Alright, perpendicular bisectors. I use the acronym PB. Which, what do you think of when you see PB? Peanut butter. A perfect bisectors. And peanut butter is very tasty with chocolate. Now, what's not quite as commonly known is that it's also quite tasty with certain veggies.
Oh, yeah.
Specifically, carrots and celery. Okay? So, peanut butter is tasty with chocolate and veggies. Perpendicular bisectors meet at the circumcenter, which is equidistant from the vertices. Okay, that one's not too bad. The other one's Alright. So, angle bisectors. This one's weird. Alright. Ab. We all have abdominal muscles. Some are more defined than others. And those are called your abs. And you have abs, which would be plural, which would use are. Your abs are defined. But maybe you only have one ab that's really defined, which means it's singular. So you would say your ab is very defined. And so we have angle bisectors meet at the incenter, which is equidistant from the sides. Close down was a stretch. Other students have said, hey, it looks like it would say abyss, so that could help you out. So whatever you want to use to help you remember, totally fine. Feel free to use those, reject those, but you do want to come up with something to commit those to. Alright, so I'm going to go ahead and pass out your homework to you. Listen up, please. Come on. Listen up, please. So your homework you see on your assignment sheet is worksheet 2, and then just the front side of worksheet 3. 3 deals with mid-segments, so I'm just going to break this up over a couple days since it's review. So feel free to do the whole thing. You'll eventually need to, but the entire worksheet 2, and then just the front of worksheet 3. I think you might need one more. You might have done. Oh, wait, one more. Oh, sorry.